Hello students, welcome to a class of topology. In this video, we are going to discuss about subbase for a topology. Okay, we will see the definition of subbase. Let X2 be a topological space. X2 be a topological space. Okay, and I take a collection of subsets of X. Let script S be a collection of subsets of X. Collection of subsets of X. We say that script S is a subbase for tau if finite intersection of elements of S form a base for tau. When you consider finite intersection of elements of script S. What is the meaning of finite intersection of elements of script S? We are taking the one element intersection. One element intersection means the elements itself. That means S is clearly contained in that finite intersection of elements of S. Then you consider the two element intersection, three element intersection, etc. And you consider all kinds of finite intersection of elements of script S. That should form a collection. This should be a base for tau. Okay, we will see one example. For example, consider real line with the usual topology. What is the usual topology to you? It is defined as set of all A subset of real lines such that for every A in A, there exists some R greater than 0 such that interval of the form A minus R, A plus R is completely contained in A itself. We proved that this is a topology called usual topology or standard topology, and every open interval in real line is open here, and which are the open sets with respect to this topology. And we already proved that collection of all open intervals form a base for this topology. Now I am looking for a subbase for this topology. Let script S is equal to collection of intervals of the form A infinity comma minus infinity to some b, where A and B are varying over real number. Okay, then I am going to prove that this script S is a subbase for this topology. So what I want to prove is, when you consider a collection, let script B be a collection of finite intersection of elements of S. Collection of finite intersection of elements of S. Then we want to prove script B is a base for tau. Then we will see what are the elements in script B. Clearly, all the elements in script S will be contained in B itself. Okay. Now, so which implies intervals of the form A infinity and minus infinity to B R belongs to script B for every A and B. Okay. Now you consider the intersection between these two elements. What will be that? A infinity intersection minus infinity to B. Okay, what is this? Okay. You consider A comma B are two elements in real line, and minus infinity to some B and A to infinity. Then what is their intersection? When you consider A is less than B, then their intersection is open interval AB. Correct? So this is the intersection of two elements from script S. So that this open interval AB belongs to script B, because script B is formed by taking intersection of elements of script S. So which implies the open interval AB belongs to script B for every A and B. Okay. And we already know that when open intervals of AB form a base for the usual topology, since collection of all open interval AB such that A and B are varying over real numbers is a base for usual topology. Base for tau u. Therefore, this script B is a base for tau u. When script B is a collection of finite intersection of elements of S, which is a base for tau u, then script S is a subbase for tau u. Subbase for tau u. Okay. Now, we know that when you have a topological space X tau, then every topology itself can be considered as a base for the topology. Correct? And what is a base? We know that base is a subcollection of tau. Now, when you have a subbase for a topology, then how will you form that base? The base is formed by taking the finite intersection of elements of script S. So the script S is always contained in B itself. So for a topological space, we can say that subbase is contained in base, base is contained in tau. This is the relationship between subbase, base and a topology for a topological space. Okay. Now we will see one necessary and sufficient condition for a subbase for topology as a theorem. It says that let X tau be a topological space. Let X tau be a topological space and script S be a family of subsets of X. Family of subsets of X. Then S is a subbase for tau. S is a subbase for tau if and only if S generates tau. S generates tau. Okay. So this is the statement. When you want a collection of subsets of X is a subbase for the topology, given topology, if and only if S generates tau. What's the meaning of S generates tau? S generates tau means tau is the smallest topology containing all the elements of script S. That is, it means S generates tau means tau is the smallest topology containing elements of script S. That means containing the script S. This is the meaning of S generates tau. Okay, we will prove this statement. First part is, when you assume S is a subbase for tau, we have to prove that tau is the smallest topology containing S. Okay, we will prove that first. Proof. Let S be a subbase for tau. Okay, so we have to prove S generates tau. That means tau is the smallest topology containing S. So how will you prove that tau is the smallest topology containing S? When you consider any other topology containing S, then that will be the stronger one. That is the method of proof. So suppose U be another topology on S, another topology on X containing S. Then we have to prove that tau is the smallest one. That means tau is the weaker topology. That is, tau is contained in U. That is, we are going to prove. Our claim is tau is contained in U. Okay. What is the topology U? U is a topology on X containing script S. Correct? So that since script S is contained in U, finite intersection of elements of S is also contained in U. Because U is a topology, every topology is closed under finite intersection. Correct? Since U is closed under finite intersection. Therefore script B, that is actually script B equal to collection of finite intersection of elements of S. Okay. If script B is like this, because script B is not given, so we are assuming script B is such collection, then script B will be contained in U. And what is script B? We have assumed that scriptus is a subbase. So the collection formed by like this will be a subbase, will be a base for the will be a base for the given topology. Since scriptus is a subbase, that was our assumption for the proof, for the this part of the proof. Subbase for tau implies script B is a base for tau. Okay. When base of the topology is contained in another topology, then the topology itself will be contained in that topology. So which implies tau will be contained in U. That means U is stronger or tau is the weaker topology, or tau is the smallest topology. Since U is arbitrary, you can take any topology other than tau. Since U is arbitrary, tau is the weakest topology containing S. Tau is the weakest topology or smallest topology containing the collection scriptus, which implies scriptus generates tau is true. Now we will prove the converse part. So conversely assume S generates tau. We have to prove that S is a subbase for tau. To prove scriptus is a subbase for tau, what we have to prove? Collection of, if to prove S is a subbase for tau, we need only prove the collection of finite intersection of elements of S is a base for tau. Correct? We need only prove, to prove S is a subbase for tau, we need only prove script to be equal to collection of finite intersection of elements of S is a base for tau. This is we are going to prove. It is a base for tau. Now, what is our collection script to be? The collection script to be is a family of subsets of X. It's a family of subsets of capital X, and which has the property that which is closed under finite intersection, because this collection itself is formed by taking finite intersection of elements of S, and is closed under finite intersection. And therefore, we can apply a theorem which was proved in the section of base for a topology, and there was a corollary. Corollary says that when we have a topological space, when we have a set X and script to be is a collection of subsets of X which covers X and which is closed under finite intersection, then the theorem says, then by a known theorem, by a previous theorem, actually it was a corollary, then by known corollary, there exists a topology, some U, because this is a topology different from tau, which is actually given by the corollary. Topology U on X such that B as base. B will be the base of B as base for U. Okay. But we have to prove that this B is a base for the topology tau. But now we have B is a base for the topology U. So in order to prove B is a base for tau, we need only prove tau and U are coinciding on X. That means tau and U are the same topology. So next we claim that tau and U are equal or equivalent. So for that we want tau is contained in U and U is contained in tau. Okay. Now we have assumed that S generates tau. That means S contained in tau, and tau is the smallest being this property. S generates tau, which implies S contained in tau. And we have script B is a base for U. And what is script B? Script B is a collection formed by taking finite intersection of elements of S. And we have S is contained in script B and script B is contained in U. So which implies S is contained in U also. So what is U? U is a topology on X which also contains script S. So which implies tau should be contained in U because tau is the smallest one. And tau is smallest with this property. So tau is contained in U. Now to prove the reverse implication, I take an element arbitrary from U. Let A be an element in U. Then what will happen? We know that script B is a base for U. Then A can be written as union of elements of B, arbitrary union of elements of B, where each B alpha is an element in script B. This is because of script B is a base for the base for the topology U, and when script B is a base, every member of U can be written as union of members of script B. Okay, and what is B alpha? Each B alpha came from script B. And what is script B? Which is found by taking finite intersection of elements of S only. So which can be written union alpha. B alpha can be written some intersection that alpha may be suffix may be different. Okay, I take it here alpha equal to 1 to n S alpha, where each S alpha is varying over script S. Right? So this is our A now. Now what is S alpha? S alphas are members in script S. And script S is already contained in our tau. So which implies each S alpha is a member in tau since S is contained in tau. And what is tau? Tau is a topology. Since tau is a topology, tau is closed under arbitrary union and finite intersection. Finite intersection and arbitrary union. Okay, so S alphas are belongs to tau. Therefore, intersection of that kinds of S alphas also belongs to tau, and their union is also belongs to tau. So which implies union alpha intersection alpha equal to 1 to n S alpha belongs to tau. And what is this A? Therefore A belongs to tau. So when you take an arbitrary element from U, then that element is also belongs to tau. So U is contained in tau, which implies if you take it as 2, then implication 2, then tau and U are same. Since script B is a base for U, which implies script B is a base for tau. When script is a base for tau, then the collection S is a subbase for tau is true. Subbase for tau. So which proves the theorem.